All right. So yeah, I'm guilty of not doing the Nyquist criteria properly last time. So yeah, I'll just finish that off maybe in 20-25 minutes or so. Yeah, later on you guys yeah, let me know need to discuss something or so tomorrow. Yeah, we need not meet. So yeah, if you guys want us to meet, then we can meet. Otherwise, yeah, I'm not insisting on having tomorrow's class. Today also just yeah, to wrap up Nyquist stability. So again, this is not part of this course, but yeah, some of you are going to see this and yeah, it is sort of part of the systems part of the course. So yeah, I thought since I started discussing this, yeah, I'll just give you a sketch of the proof. Okay, so if there are no questions, then let me start. If there are any questions or comments, yeah, feel free to.
Sir,
Yes.
there is this Nixist is it not part of the syllabus for the exam?
Uh, yeah, I'm not going to hold you responsible for it in the exam, but it's better that you know it if you are from E or instrumentation. You are going to see this later. But yeah, I mean, NSEM I will not hold you responsible for Nyquist criteria. Nyquist sampling criteria is there, but not the stability one, which I'm going to discuss today. Any other questions?
Can you repeat what you have said just now?
Okay. I was saying that Nyquist sampling criteria is there in the exam, but not the stability one. Okay, so I am discussing it as a part of this course, but yes, I will not hold anyone responsible for it in the NSEM exam. Okay. So it
Yes,
is,
sir.
yeah, yeah. So it is also there in the last chapter of Oppenheim. So yeah, it is a part of signals and systems, but yeah, not for exam. Okay. So let me start. Last time we discussed a little bit at least. So let's recall some of the things and let's complete our understanding from where that Nyquist criteria comes from. So it is basically to check stability of the closed loop system. So yeah, this is your open loop system transfer function. So G is the transfer function of some open loop system. There is no feedback yet, and G is assumed to be strictly proper. So what I mean by that is numerator degree is strictly less than the denominator degree. Okay. So that is one of the underlying assumptions, G being strictly proper. We will see where that comes into play. Okay. And then the closed loop transfer function looks like this. Okay. G over 1 plus G. So we are considering unity feedback. So this is closed loop transfer function when there is a unity feedback. We can take a general transfer function here also, but yeah, let's start with unity feedback and yeah, then we will see how that extends to non-unity feedback models, etc. So this is okay. So whether the open loop system is stable or not, that is determined by roots of the denominator polynomial, right? So if the roots of the denominator polynomial they lie in the right half plane, then of course the system is not stable. Open loop system. I mean. Yeah. I hope that is fine with all of you. We have studied this. Okay. What about stability of the closed loop system? So the closed loop transfer function is given by this. So let's try to find out poles and zeros of the closed loop transfer function. So let's substitute n over d for g. Here we get this simplifies to n over n plus g. So these are poles of the closed loop transfer function 1 over g over 1 plus g. Yeah. So these are poles of the closed loop transfer function, and d of s gives us the poles of the open loop transfer function. Okay. Let's also make note of one more thing. Consider this function 1 plus g, okay, which was the denominator part of the closed loop transfer function. Okay, and let's denote zeros of this transfer function by z. Okay, and poles of this let's denote that by p. So capital Z denotes zeros of this transfer function, and capital P denotes poles of the same transfer function. Okay. So poles of this and poles of the open loop transfer function are the same, right? Because poles of open loop transfer functions are also P, and poles of 1 plus G are also P. So we will be dealing in the proof of the Nyquist criteria. We will be dealing with these two quantities. Okay, zeros and poles of this transfer function 1 plus. Okay, so any questions so far? This should be clear to all of you. Pretty straightforward. Just manipulations, basic manipulations. Alright, so I don't see any questions. So let me go ahead. Okay, now we, like I was saying last time, we are going to relate the number of encirclements to these Z and P quantities. So this is what we are after. We are trying to prove this. This sign, just be careful. Sometimes it is P minus Z also. Okay? So depending on your orientation, it is Z minus P or P minus Z. Or here you have an alternate sign or something. Okay? But this is what we are trying to prove. So this Z and P come from the poles and zeros of 1 plus GS. And Z you can associate Z with the poles of the closed loop transfer function as we have seen here. And P is the poles of open loop transfer function. N is the number of encirclements of the frequency response about some point, okay, origin or -1. I'll come back to this later. But I hope, these things are clear. What we are after, and what are these underlying entities? So, any questions on what capital N is, capital Z, and capital P? Capital N will become clear in a moment if it is not clear right now, but hopefully this is fine. Okay, so let me start. So last time, yes, we were discussing this winding number phenomena. So before that, I want to recall just a couple of things. So first is the definition of the winding number. So if you are given any closed curve, so we are starting with a unit circle, okay, which encircles the origin once, okay, and inside the integral we have this function 1 over z, which has a singularity at the origin. Okay, so this is not complex differentiable at the origin. So except the origin, it is differentiable everywhere else. So that's what we mean by having a singularity at the origin. And now if we integrate, if we evaluate this integral, what we get is the number of times this curve winds around the singularity. Okay. So we saw last time that if we parameterize this unit circle like this, so by e to the power I theta, I going from 0 to 2 pi. So when we do this parameterization, when theta goes from 0 to 2 pi, we end up having one one round okay, around the origin with this parameterization. Okay, so this parameterization winds around this singularity once is what this means. And if you evaluate this integral, you can check that you get 1 as the answer. Okay, so just go through this simple manipulation. This is already uploaded in the file section. So the integral evaluates to 1, okay, with this parameterization. Now if we change the parameterization, for example, e to the power I n theta, then when theta goes from 0 to 2 pi over n, this parameterization completes one circle, so one trip around the circle. And as theta goes from 0 to 2 pi, it completes n rounds around the origin. And you see that n coming out in the by simplifying the integral. Okay, so that also you can check. Just straightforward substitution. So given any curve which winds around a singular point, this integral evaluates how many times that curve winds around the singularity. Okay. So this need not be a unit circle. This could be any closed curve, and the point could also be anywhere, not necessarily at the origin. Anywhere in the complex plane, you have a singularity, and if you integrate this function over a closed loop around the singularity, then what you get as a result of this integral with 2 pi I factor outside, the number of times the curve winds around the singularity. Okay. So that is a fact from complex analysis, and that's what we call winding number. Okay. So in general, given any curve gamma, this quantity gives us the number of times gamma winds around the origin. Okay. So this will be crucial while proving this Nyquist criteria. Okay. So if you understand this, then you are sure to understand the sketch of the proof. So any questions regarding this so far? Alright, so let's take a small detour from this and we will come back to this in a moment. So let's go back to this figure. Okay. Alright, so this is the purely imaginary axis. So this is I omega or j omega. And this is an infinite semicircle, okay, r tends to infinity. So entire half plane, right half plane, we have included in this infinite semicircle. Okay, so this is the purely imaginary axis, and then we have drawn this arc at infinity. Okay. Alright, so this curve I am going to call this small gamma. Okay, this infinite semicircle, the entire purely imaginary axis, and along with this arc, that I am going to denote by small gamma. Okay. So there are poles and zeros of 1 plus g inside this contour. Okay, so this closed curve I am referring to as contour. There are poles and zeros of 1 plus g in the right half plane, which are of interest to us. So poles I am denoting by cross and zeros by a circle. So just for simplicity, I have just drawn one pole and one zero. Okay, there could be multiple such poles and zeros. This is just for the sake of simplicity. Okay, so now I am going to uh, evaluate g on this contour. Okay, so let's evaluate this one, g of gamma. What do I mean by that? Is evaluate g. So g of s, you substitute for s, all these complex numbers. So that's what we mean by evaluating g on gamma. We are evaluating g on this big semicircle. So let us see what we get. We'll get some curve, and that curve I'm going to call as capital gamma. Capital gamma is something like this. So this is image of small gamma, okay, under G. Yeah, I will write 1 plus G. Okay, so let us see what this thing is. So G, if we when we evaluate it on the purely imaginary axis, we just get the frequency response. Yeah. G omega is just the frequency response of G. So let us see what happens at this arc at infinity. Excuse me. Okay, so we have assumed that G is strictly proper. Denominator degree is strictly bigger than the numerator degree. So at infinity, yes, R is going to infinity. Yeah. So of course, G is going to go to 0 because the denominator degree is strictly bigger than the numerator degree. So you can see that this term goes to 0 at this arc. Okay. So when you evaluate G on gamma, the only non-zero contribution you get is from this quantity, G omega. So the semicircular arc, you don't get anything from this because the contribution is 0 from that, because R goes to infinity. The power of R in the denominator is bigger than its power in the numerator. So yeah, this is going to vanish along all points on this arc. So these points will survive. All these points they vanish. Okay. So let me draw an arbitrary shape of G omega. Okay, it may not be like this, but I don't know. Just for the sake of drawing, I am taking something. It could be symmetric, but yeah, not drawn it symmetrically. So omega going from 0 to infinity, maybe you can draw the frequency response for that, and yeah, omega from 0 to minus infinity is just by symmetry you can complete that. And the contribution from the semicircular part is 0. So that does not contribute anything. So this is what gamma looks like. Okay, maybe so that it looks more symmetric. Okay, so this is capital gamma again in the complex plane. So this is my complex plane will be so small gamma was this big semicircle with poles and zeros of 1 plus G in the right half plane, and we have mapped this contour onto capital gamma, which turns out to be 1 plus the frequency response. So you plot the frequency response and just shift it by 1. So it looks like this. The contribution from the semicircular part is 0. All right. So if that is clear, then yeah, we are one step closer to proving this. So this is what it is. Capital gamma is 1 plus G gamma. And now, yes, let's look at this integral. So d omega over omega and closed loop integral over capital gamma. Okay. So note that we are integrating with respect to this loop, capital gamma, and not the small gamma loop. Okay. So this quantity gives us the number of times the frequency response. Yeah, this frequency response winds around the origin. Yeah. If it does not wind around the origin at all, you will get 0 at this integral. But yes, 0 may be inside the loop, in which case, yeah, you will have a non-trivial winding number. So this is the number of times gamma or g of j omega points around the origin. G of j omega or 1 plus g of j omega. So that is capital N. So that's what this N is. D omega over omega or dw over w, closed loop integral over capital gamma. So now for capital gamma, I can substitute f composed with small gamma. Okay, what is f? F is yeah, just 1 plus g. Okay, so this 1 plus g gamma, this I am writing as f of gamma. Right, so this integral is same as f composed with gamma, the same integral. And now you can note that if we write this integral, closed loop integral over gamma, f prime df over f. Okay, in this integral, if I substitute f is equal to w, yeah, then f prime df is going to give me dw, and yeah, instead of integrating over gamma, I'm going to integrate over f composed with gamma. Okay. So you can see that these two integrals are also equal. Okay. From here to here, just substitute f composed with gamma, then write down this integral, and from here to here, yeah, I've just explained how to go from here. Substitute w for f. So that's why this integral is same as this integral. Okay. So this integral we have already seen, it is capital N. Yeah, it's the winding number. And this integral, in a moment we will see it is z minus b. So any questions so far? All right. So yeah, the next step is going from simplifying this integral, which turns out to be z minus b, and that follows from argument principle. Okay, so let me open the argument principle from Wikipedia. So it will. I will also show you where that g minus z comes into play. Okay, so this is what argument principle is, and understanding this is also not too difficult. So yeah, let us see where these things come from. Okay, so note that we are trying to simplify yeah, this integral f prime df over f. Okay, so let's assume some form of f. Okay, so let's write down f in terms of its power series. Yeah. So suppose f has a 0 of multiplicity k at this point, z sub z. Okay, so there is a 0 of order k. So f of z, let's suppose we can write that as yeah, just take out this factor with its multiplicity, such that g of z does not have any 0 at z sub z. Okay, so all zeros at z sub z you have taken out in this factor. G is non-zero at z sub z. If f has such a 0 at some point, you can write down f of z in this form. I hope this is fine. And now if you write down expression for f prime, this is just applying the multiplication rule of differentiation. So you differentiate this first, keeping g as it is, and then you differentiate g. Okay. and then if you write down f prime over f, that turns out to be this quantity, okay, k over z minus z sub z and g prime over g. So now we want to recall one fact from complex analysis, which is as follows. Okay, so if you have a complex differentiable function, so if f is complex differentiable, that means those Cauchy-Riemann conditions must be satisfied for real and purely imaginary part of f. Then the closed loop integral of f over any closed loop is 0. Okay, so this is a fact from complex analysis, one of the basic results of complex analysis. Okay, if you have a complex differentiable function, then over a closed loop, its integral is 0. And, we are going to use this fact in understanding this quantity. Okay. So both, so G, we saw that G does not have any 0 at z sub z. Yeah. So this quantity G prime over G of z, yeah, z sub z. If you let me draw some picture. So imagine this point z sub z, and we are taking integral around a small contour around that point. Okay, so there are no more singularities, just this singularity. And now if we integrate f prime over f over this contour, then there is a singularity of this function. Okay, but this function has no singularity. This is complex differentiable. So this is going to evaluate to 0 because g prime over g has no singularity. When we integrate f prime over f over this small curve, what we get is k. So if there are k zeros of f, yeah, then such closed loop integral is going to give you the number of zeros encircled by this loop. Okay, so there are k number of zeros, so you will get k when you do this. Okay, so that's when f has a 0 of multiplicity k. So let us see what happens when f has a pole of multiplicity m. Okay. So just following the same logic, yeah, you can write down f of z as z minus zp to the power minus m. So this indicates pole at zp, such that h of z has no poles at zp. Okay, and just go through the same algebra. You will see that f prime over f integrated over a contour like this, which now contains zp instead of zz. But the integral has a negative sign. Okay, so when you do integrals like this for poles, you get minus sign, and for zeros, you don't get a minus sign. Okay. Alright, so this is the argument principle, and now we are almost there. Okay. So let us see how to reduce our case to this these simple cases. Okay, having just single poles and zeros instead of multiple poles and zeros. So we saw that inside gamma, small gamma, we have multiple poles and zeros. Okay, and instead of doing this, we somehow want to simplify our task. And, that also can be done with this simple trick. So your original curve gamma, you can split it like this. Okay, so suppose there is just one pole and one zero for simplicity, and suppose this is the entire curve gamma. Then you can trace around these points. Okay, then go back. Likewise here also trace around the singularity. So we are cutting this singularities out in this. So we have cut out these two circles, okay, from gamma, and then we are adding them back. Okay, so the original curve gamma, we have split it up into these parts. So this one curve with okay, these holes in the middle, and we have added back these holes. So the integral over small gamma can be rewritten as integral over this shape with some holes, and you also add back those holes to get the entire shape back. Okay. So these orientations, okay, these curves cancel one another because you go downward and then you come back likewise here, here, etc. So these things cancel, and yeah, what is left is the outside with these holes inside which are cut out. Okay. So what about this shape now? We have removed the singularities. So uh, function g, since all poles and zeros are removed from this region, is well behaved inside yeah, this region with holes. Okay, so go back. Yeah. So this integral now we are writing as, let's say, gamma prime plus gamma prime plus small discs, okay, small circles which are cut out from gamma. Okay. So gamma prime is yeah, this region with holes, and yeah. So integral over gamma prime is going to give 0 because there are no singularities inside gamma prime. Whatever singularities are there, we have removed them, and here we are adding them back. Okay. So you'll get contributions for all zeros which you put together inside one term, and you'll get contribution for all poles which you put together in one term, and that's where these two quantities come from. We are already seeing where n comes from. Okay. So I hope this is fine. So Z is the number of closed loop poles in the right half plane. P is the number of open loop poles in the right half plane. So this is not all poles, okay? Just the poles in the right half plane, because yeah, we started with a contour like this, where we only consider poles and zeros of 1 plus g in the right half plane. So Nyquist stability criteria tells you that number of times your frequency response winds around the origin is same as number of closed loop poles minus the number of open loop poles. And now instead of 1 plus g, you can just you can get rid of this one factor and find the winding number of g of gamma, and instead of origin you find that around minus 1. Okay. So number of times the frequency response wind around the point minus 1, that is n, and that is same as z minus 1. Instead of doing 1 plus g, you are just, excuse me, you are evaluating g, and you are finding how many times that winds around minus 1. So that is just a shift factor. It's not a big deal. Okay, so let me state this again. This is the number of times the frequency response winds around the point minus 1. Z is the number of closed loop poles in the right half plane, not all poles, but just the number of poles in the right half plane, and this is the number of open loop poles in the right half plane. Okay. So we started with the open loop transfer function G, which had some poles, okay, out of which maybe P of them are in the right half plane. And if we find the frequency response of G and see how many times that winds around the point minus 1, we can find n, and then from n plus p we can find out whether the closed loop transfer function has any poles in the right half plane. Okay, so that is given by z. And yeah, taking this slightly further, instead of unity feedback, you can have something like 1 plus gh, where your feedback is given by transfer function h now. Okay, I think this is also h, maybe just check whether it is h or not. Yeah, I think it is h, gh over 1 plus h. And instead of finding the frequency response of only g, you find frequency response of gh. So g of j omega times h of j omega, and that frequency response, yeah, you see how many times it winds around the point -1. Find out how many poles g times h has in the right half plane, and then n plus p will give you if this closed loop response has any poles in the right half plane. So from that you can conclude whether the closed loop system is stable or not. Okay. And for varying gain k also, you can have a k factor here, and then you can take out k, and you'll have 1 over k in here, and instead of finding encirclements around -1, you find encirclements around 1 over 1, sorry, -1 over k. Instead of -1, find encirclements around. So yeah, there these are like straightforward generalizations for more general cases. So the idea is yeah, to check stability. And how do we check that? Whether the system with feedback has any poles in the right half plane. So Nyquist criteria allows us to find the number of poles in the right half plane when there is a feedback. From that we can conclude the stability of the system. Alright, so that is all I had to say. Any questions or comments? I think that is the last thing I want to do, like with stability. Hope this is fine with everyone. Alright, if there are no questions, then yeah, I think this is where we end this course. Then maybe I'll show you one picture of the courses maybe which you can do after doing this course. I don't know whether it is helpful or not, but just for the sake of it, maybe I'll show it. Okay, so there are many courses you can do after this. So we are here, signals and systems, and yeah, you can do courses on wavelets, harmonic analysis. So this is those who are interested in maths and stuff. And you can also do image processing and DSP courses. Okay. Signals and systems background. You can also do systems and control, multidimensional systems, etc. Then data science, graph signal processing, machine learning, etc. So there also you'll run into these things. Okay, feature extraction, etc. So that's sort of like decomposing your whatever data into basic building blocks. Okay, so there are similarities with signal decomposition and so forth. Okay, things like SVD and so on, and yeah, more sophisticated versions of SVD. Yeah, then circuit theory, power electronics. Yeah, Here also you'll see some applications of filter theory, etc. Yeah, proper courses on analog filter design and so forth. Yeah, estimation and statistical signal analysis, probability random processes. So we have not considered any probabilistic signals and probabilistic models. So signals with noise and so forth. Basically, we only dealt with deterministic quantities. So yeah, stochastic quantities, etc. This is, I think, yeah. So immediate next course is yeah, either a course on estimation or a DSP, image processing, etc. Even wavelets, maybe wavelets after you have done some DSP. Yeah, and this is also something if you are interested in communication, then information theory and communication. Also you can pursue. Okay, and your toolkit which you may want to build is this. So expertise in these things will be handy if you explore most of these topics. Okay, things like linear algebra is sort of necessary, probability and statistics also, optimization, algorithms, numerical computation. This is if you want to go a bit advanced. Graph theory is sort of required maybe. Yeah. But functional and harmonic analysis, if yeah, if you want to dig deep into like in specific area. But in general, I think yeah, linear algebra, probability, optimization, algorithms, graph theory is good enough. Basic circuit theory, I think yeah, you have already done that in first year course. Yeah, and related areas, whatever. Okay, so what let to say? I don't think I have anything else to say. Just want to thank everyone. Everyone has been super cooperative. Just that, yeah, there was a lot of enthusiasm last year compared to this time, but it's okay. Fine. I hope you guys had at least something to, at least some takeaway. Yeah, I hope I have not bored you to death. I mean, sometimes, yeah, most of the times I came not like fully prepared, etc. Yeah, I'm like those of you guys who don't come fully prepared for their exam. So yeah, I'm also like that. So yeah, sometimes that's why I get stuck during lectures and yeah, I forget things. So yeah, but hopefully I have later on explained things. Yeah, so that I've made up for the mess. At least I've tried to made up for the mess I did in the previous class. Hope it is fine. Okay, that's it from my side then. If anyone has any comments or suggestions, so I said this, I think few weeks back also. So this feedback, okay, so yeah, in this system also we need some feedback so that, okay, it works to everyone's advantage. So feel free to give feedback so that I know what input to feed into this system if I take this course next time. All right, so if there are no questions or comments, then we can end here.
Oh, sir.
Yeah.
Sir, please mail us the syllabus for the test.
Okay.
Yes, sir.
Okay, so up to sampling, everything is there. But yeah, anyway, I will email them.
Okay, sir. Thank you, sir.
Thank you, sir.